Hey guys, Miss McCorn here. Today I'm going to show you, this is probably just kind of a quick and easy one. It'll be a long video, but there's not a whole lot of practice that we're going to do tomorrow with this, and we are almost done with Unit 5. This is 5.5, 5.6, and 5.10, so go ahead and pause the video so you can look at these learning objectives. Alright, so the first thing we want to look at is there are three things that affect the reaction rate. We need to make sure that there is a certain number of collisions happening between the reactants, and they have to be with a certain orientation, and they have to have a certain energy in order to produce the reaction. So that energy is called the activation energy. So as the concentration of the reactants in a liquid or gas phase increases, that makes the collision rate increase. Another thing that can increase collision rates is the surface area. So the more surface area you have on a reactant in the solid phase, so if you crush something up into a nice fine powder, that is also going to increase the reaction rate because more collisions are going to be able to occur between the surface of the molecules. So also when you increase temperature will increase the kinetic energy of the molecules, causing them to hit with more force. So you're increasing the average velocity. And therefore, you are actually going to increase the energy of the collisions, which is one of those rates that affect those reactions. All right, this is what we mean by collision orientation. So not every time that the molecules collide is going to have a reaction occur. So they actually have to hit each other in a specific way. So unless they hit each other in that specific way with the activation energy overcome, that is the only way that a reaction can occur. Otherwise, as you see in this top diagram, a reaction will not occur. If you look here, this is called an energy reaction a reaction energy profile diagram. The x-axis is the reaction coordinate, and you do need to know the this vocabulary, the reaction coordinate and the transition state, so just make note of those. And we will get back to both of those vocabulary words. So you notice those are still circled for a good thing. At the top here, you'll see kinetic energy right here, okay? And our kinetic energy is what your top up here in the transition state. So when they are in this transition state at the top of the curve, that is when they have the most potential energy. They are actually taking their kinetic energy that they have when they run into each other here, and they're converting it into potential energy in the bonds. So in this particular case, what's happening is C is forming a new bond with B, and A, the bond between A and B, is lengthening. So all right, so what we have here in this transition state is when the potential energy has reached its maximum, because the potential energy is contained within all of the bonds, A, B, and C. And what we have is an extremely unstable aggregation of all the atoms that are contained in these reacting molecules. And then what we have is this downward slope here. And this downward slope, the potential energy begins to drop considerably. The electron density between B and C starts to increase. So you have lots of electrons gathering between B and C, so this bond length here starts to shorten. And then you also have the bond between A and B. And the electron density there actually decreases, so the bond's going to continue to stretch, and this is going to break apart. So then what you have at the end here is the graph is starting to plateau. And what you have here is a very stable potential energy, and we have the potential energies locked in the bonds here between B and C. All of this actually happens in about 1 × 10⁻³ seconds, which is obviously really fast. What you also need to realize here is that we have this EA. This is our activation energy, and that's how much energy it takes to have the reaction occur. And we are going to come back to that. So if the energy of the collision is less than the energy of the reaction, of the activation energy, you're not going to have a reaction. So if you looked at our last slide over here, we had the energy of the collision was greater than the activation energy. So when the energy of the collision is greater than the activation energy, it can go over that hump. But what we have in this particular case is we have the energy of the collision is less than the activation energy. So in this particular case, a reaction is actually not going to happen. So these may start to lose their, gain some potential energy when they collide. But what we have happening is they actually just return back to reactants because they do not have enough energy to produce products. So they'll temporarily bond, but then they're going to go right back. Okay. Another thing we want to look at here is this Maxwell-Bolton distribution. So this is really similar to Maxwell-Bolton distribution. What we're looking at here is the collisions and the collision energies. So what we see here is the kinetic energy, and as the you'll notice as the temperatures increase, we have more particles on this curve. We have much more particles that have enough energy to collide and cause a reaction. At lower temperatures here, more of our particles are going to be at a lower kinetic energy, so we will not have as many collisions having enough energy to cause a reaction. This is one of those just FYIs. For any of those unimolecular decomposition reactions, the energy required to break the bonds in the reactant is actually obtained when they collide with a background or solvent particle. So what you'll see here, this M that you see in the equation, that's our background or our solvent particle. Okay, I told y'all we would go back to activation energy. So our reaction rate depends on the magnitude of the activation energy. So how big is this hump that they have to get over? So if we have a very large or high reaction or activation energy, usually the rate of the reaction is going to be fairly slow. And if we have a faster reaction rate, generally it's because our activation energy is lower. That way it's easier to get over this hump. That means it doesn't require as much energy for our reaction to occur right here. Okay, quick summary of what we've done so far. There has to be a collision. The collision has to occur with the correct orientation to cause the reaction, and the collision energy of the collision has to be greater than or equal to the activation energy. You'll notice here we have two types of reactions, endothermic and exothermic. You'll see the definitions are right here. In an exothermic, that is where we have energy being produced. The bonds in the products have less potential energy than the bonds of reactants, so there is energy released. And then endothermic is the opposite. The bonds in the products have more potential energy than the bond in the reactant, so we actually have energy that's absorbed. Generally, I'm sure that you know that exothermic usually gives off heat and endothermic usually absorbs heat, so you'll usually feel cold if you have an endothermic reaction. When you have an equilibrium reaction, you'll see that we have forward and reverse reactions. So the activation energy value is going to change for the reverse reaction. It's actually going to take more activation energy to get back over that hump for that reverse reaction. You'll notice here, this is our activation energy. So you'll notice that this arrow is much larger than this arrow here. So to go in reverse in this particular case, it is going to take more energy to get back from AB plus C back over to A plus BC. So just keep that in mind when you're looking at these forward and reverse reactions that have those double arrows in them, our equilibrium reactions. What this does mean when we have a reverse reaction that requires more energy than our forward reaction, what this does mean is that they're going to have to collide with greater energy or greater kinetic energy in order for the reverse reaction to actually happen. So when we have multi-step reactions, you'll see step 1 and step 2, and this right here, you might want to pause the video and just take a look at how this looks. You'll want to be able to identify whether the first step and second step are endothermic or exothermic, and then once you've determined that, you'd be able to find out what the activation energy is for each, which is the slow step and which is the fast step. All right, and you can see I've written here in step 1 we have an exothermic reaction, and that is because our products have less PE in their bonds. And in step 2 we have endothermic for the opposite reaction. So now I'm going to show you an example, and I'm going to have you answer a couple of questions about that. Okay, here's your multi-step reaction energy profile that I want you to answer these Edpuzzle questions about. Now, when you come in tomorrow, go ahead and pause the video. And when you come in tomorrow, we're going to talk about this super exciting Arrhenius equation, and I will go through examples with this